So far in this series, we have used Homotopy Type Theory to describe logic, arithmetic, and topology. In this video, however, we are going to venture into the world of algebra. We are going to define monoids. But first, we have to go back to propositions. Recall that in classical logic, a proposition is either true or false. In homotopy type theory, this is like saying that we cannot distinguish between the inhabitants of a proposition. They are all equal. For example, if the proposition A had this property, then given any 2 points in A, we can construct a path between them. We call these propositions mere propositions. A mere proposition is almost the same thing as a contractible type, except that it doesn't need to have a center of contraction. In fact, it can be completely uninhabited. We can now use our definition of a mere proposition to define a set. A set is a type whose equality types are all mere propositions. This means that a set doesn't have any holes. That's why we can say that the natural numbers form a set, but S1 and T2 do not. Using our definition of a set, we can now define monoids. Suppose we were given a type S, a term E in S, and a function mu used to compose terms in S. We say that they form a monoid if S is a set and S, E, and mu obey what we call the unit laws, and S and mu obey the associative law. But what does this all mean? Well, suppose S were the natural numbers, E were the number 0, and mu were addition. We say that 0 obeys the unit laws if, given some number A, 0 plus A equals A, and A plus 0 equals A. And we say that addition is associative if, given some numbers A, B, and C, A plus B plus C equals A plus B plus C. Finally, we say something is a monoid if it inhabits the following type. There exists a type S, a term E in S, and a function mu composing terms in S, such that S, E, and mu obey the monoid laws. We now know how to define a monoid in Homotopy Type Theory. Thanks for watching.